Hi, my name is Tom Tranter. I'm from UCL, and this video is going to be explaining some of the advanced examples of PyBaMM. So first of all, I'm going to tell you a little bit about some of the research that I've been doing over the last couple of years, which is using PyBaMM to essentially model slightly larger systems than we might be used to. Taking the 1D model and scaling it up. And the first example of this is actually using a tomography image of the inside of a cylindrical cell, and we call this picture here jelly roll. What it is essentially the two electrodes that are a very long sort of piece of material to start off with. Maybe for an 18650 each one is about a meter long. For a 21700, maybe a meter and a half, and then for the newer 4680 format that's being proposed, depending on the electrode thicknesses, it could be up to 5 meters long. And once the sheets are put together with separators, they're rolled up and then stuffed inside of a can. Tabs are inserted, it's sealed off, and then you have your battery. So this is a 2D slice of such a battery. And we can see that when we scan the battery in a tomography machine, we can get quite a nice picture of the whole cell, depending on the resolution and the machine that we use in our lab. And we can actually go to much finer detail and get down to nanometer resolution. This is micrometer resolution, so we can get a picture of the whole cell. And the computational domain for the model is extracted from this image. What I mean by that is basically the current collectors are identified, and they are essentially represented as a resistor network. So you can see red and blue there for positive and negative electrode current collectors. And then around the roll, I've designed a sort of spiderweb mesh where at each node you actually have an electrochemical simulation being provided by PyBaMM. So in this particular example, there's about 1,300 individual models, and they each run in a sort of self-contained way, with the boundary conditions being set by solving the global current problem on the larger network, and also a thermal problem. So where you see connections in the network there for resistors representing the current collectors, that same topology is used to actually solve a thermal problem. So you can essentially apply the same sorts of principles. So where you might have Ohm's law for current, you have Fourier transport, which follows a similar linear relationship for the thermal conduction. We're assuming that the center of the cell is thermally insulated, and then the heat loss is occurring at the outer edge where you see those green nodes. So that's where we apply the boundary conditions for the thermal problem. In yellow, these are the boundaries of the electrodes where the current boundary conditions are applied, and the voltage boundary conditions, depending on whether you're doing galvanic or potentiostatic. And each layer has a sort of two ends where we assume that there's going to be a positive or a negative tab either on the inside or the outside. And the model actually doesn't explicitly resolve those tabs. It could do, but here we've just used the network representation, and it allows you to actually pick where tabs might be just by selecting nodes individually. So in the paper that goes into more detail, we looked at the effect of having one tab on each electrode or 5 tabs, and then in a study I'll come on to in a little bit later on, we actually looked at the new Tesla kind of infinity tabs, where you more or less have a tab at every single position around the jelly roll. So coming on to some of the results that you can get from this is actually showing that Tesla paper now. And you can see on the left, I've highlighted where, for the two scenarios where you'd have just a single tab or tabs anywhere by this dark region. And then this middle picture, over time, you can see that the current collector current density has an average value, which is the solid line. So we're just doing a constant current discharge for this simulation. But then the dotted lines are the global kind of minimum and maximum. And these cases here, A, B, C, D, are for different heat transfer coefficients at the outer edge of the cell. So on the left-hand side, you have standard tabs, and on the right-hand side, you have the Tesla tabs. And you can see that given the same average current for each case, the variation with the Tesla tabs in that local current density is a lot smaller. So you're only ranging maybe 10% or 20% at the end of your average, whereas here at the start and end, you've got a deviation of the minimum and maximum being at sort of 100% or even larger. So what that means essentially is as you're charging or discharging, certain regions of your cell are going to be working a lot harder than other regions at different stages in the discharge in the cycle, and that's going to have a knock-on effect on local degradation mechanisms that might be C rate dependent. And it also has the tab architecture also has a profound effect on the thermal transport. So you see on the sub-figure E down here on the left, that large sort of pinkish region is all down to ohmic heating in the current collector. So when you only have a tab at each end and you've got a very long roll, such as you would have in the 4680, you actually get quite a lot of ohmic loss, and that generates heat. And it's actually surprising for this cell. You've got these current collectors that are basically aluminium or copper, which are very conductive, but because they're quite thin, they're only 10 or 15 microns thick and very long, you actually get quite a high resistance in them. And then when we see the Tesla tabs, the current isn't really having to travel around the roll at all. It can basically just go in at the top of the cell and then conduct down the height of the cylinder. So that ohmic loss is completely negated, and you get much less heat being produced, and therefore a lower temperature. So you can see at the end of discharge here for the standard tabs, worst case scenario where you've got minimal heating, you can get up to about 80 degrees higher than your initial starting temperature, whereas with the Tesla tabs it's more like 20, 25, which is quite a significant difference. And we can also use this framework to basically investigate current and thermal problems in packs, and that's what we've done here. So we actually built a rig, and we had 32 21700 cells in a 16 P2S configuration. We had buzz bars that were in this kind of interdigitated design. So you can see that on the positive tab, it's connected to cell 1, 2, and 3, and 4, etc. And then cell 1 is actually in series with cell 17. And likewise 2 with 18, and so on and so forth. And that's a little bit clearer on the bottom right schematic, which is represented by LT-SPICE. And using LT-SPICE or Simulink, we can kind of apply the same principles as we were doing for the jelly roll. We can solve the current problem on the global network. The thermal problem in the pack at this stage is a more simplified example. So we're just assuming that each cell has its own lumped thermal interaction with its environment, and there's no cell-to-cell interaction. Whereas with the jelly roll, neighbouring sections of electrode can influence each other, thermally conducting outwards through the whole mesh. And you could introduce other things, other similar mechanisms in the pack, but for the moment we're keeping things simple. But the heat transfer coefficient is pack position dependent. So you have air flowing from left to right. So the cells on the left are going to experience a greater amount of cooling than the cells on the right, as the air will simply be cooler and the temperature difference between them will be greater. So we did some CFD to sort of calculate those heat transfer coefficients and validate the model. And then we ran the rig and we ran the simulations through a number of different scenarios where we were charging and discharging at different C rates. And we also put it through a WLTP duty cycle. And you can see here an example of a simple constant current to charge, followed by a rest period, followed by a constant current discharge, followed by another rest. And this is the experimental data that we're showing in this image on the right, this video. You can see the heterogeneity in the cell voltages and also the cell currents and the cell temperatures, as I was saying. And so you can see that there's quite a range in temperature, actually, just mainly dependent on the pack, but also dependent on which particular cell is experiencing the highest load at any given moment. And temperature affects the internal resistance of the cell. There's a certain point where it's good, and the cell operates a bit more efficiently, but then temperature's not necessarily a good thing in general for degradation. And future work is going to be basically including degradation models in this work, and then running the simulations for much longer and seeing whether we can pick up any pack position dependent degradation. On the bottom right there, we've got just a comparison between the pack terminal voltage between the simulation and the experiment, and it's not quite showing an exact match towards the end where you have the relaxation of the final step. It's actually because it's at the end of the voltage, it's sort of the end of the minimum voltage range. There's quite a steep drop off there at the end. So any slight variation or uncertainty in state of charge is actually going to manifest in quite a big voltage difference. But we seem to be getting a really good match for the rest of it. It just might be that over time the actual capacity is changing. For the battery, we've already only run it for a few cycles, but seen quite a bit of degradation, and the model needs a little bit of improvement to capture that. And that's all I wanted to say about that particular model. And I can show you it working. We have built some software. It's not quite ready for release yet. But it's going to be an additional package to PyBaMM. Currently calling it Line Pack at the moment. That may change, may become something like PyBaMM Pack. Not quite sure yet. But essentially, we want to be able to reproduce a lot of the functionality that you can see around the experiments in PyBaMM. So to be able to give it an experimental protocol, and then either use the netlist or generate the sort of pack topology parametrically with an input variable of number of cells in parallel and series, and then essentially solve the problem globally and introduce the thermal problem as well in the same way. But we can see here, see the script in action. So this is for the 32 cell setup that I showed you earlier, and I can run it, and we can see it's solving very quickly. So we've got the process that it follows is it steps the electrochemical models by a small time interval with a fixed current and a fixed temperature, and they are determined as inputs to the model. And then what it does is it iterates the electrochemical models, gets a new value for internal resistance and state of charge, calculates some heating terms, updates the temperature based on the thermal model that you use, and that can be done completely in PyBaMM, or it can be done with an external sort of model, either one that you might code yourself, or you could put this in Simulink and use their thermal modeling. And then on the next time step, it uses those new state variables to solve the global current problem again, provides new currents to each of the batteries and iterates in that fashion, in that sort of seesaw global and local calculation fashion. So here I've got a reasonably large busbar resistance, and we can see that there's quite a big variation in the cell currents, and that manifests as well in a variation in terminal. So this is accentuating it a little bit more than the experimental results that I was showing earlier. And again, you can see those temperature differences. And so the final thing would be to implement it in Simulink. The advantage of this is that you can bring in other modules inside Simulink. But unfortunately, we found that the way that we've implemented it is slightly slower than doing everything in Python, and that's just a case of the way that basically Python and MATLAB don't really like talking to each other that well at this point. We're working on getting everything a little bit more robust, but essentially the method that I've used to couple the two together is to use the Casadi solver, generate an integrator and a variable evaluator function in Python, and then load those into Simulink. So we have the battery subsystem objects, and inside here you can see it's basically just a voltage source and an internal resistor, and then what sets those two values, there's a script which is interpreted, execution, and inside the script there's a lot of stuff about setting the number of input and output variables. Essentially, it's the same process. The two inputs are temperature and current, and the outputs are voltage and resistance, and then whatever other output variables you might be interested in. But then essentially what it's doing is initializing itself, loading in that integrator and that variables function, and then iterating its own self with new inputs and outputs, just calling those two functions. So it's quite a simple thing to set up and run, but there are nuances in terms of getting it to run really efficiently, and we haven't found a super way to do that just yet, but it's a work in progress. And this code, this small example code here, will be available on GitHub shortly. We're still going through some testing internally on that, but again, I can show you it running. So just by a simple script, it actually there's some Python code that's defined in a separate script, and that basically just sets up the models and the parameters, so it defines the cell, and then auto generates those integrator and variable functions, and then the rest of it is basically just reading in some common parameters and doing some calculations on the battery cooled surface areas, so that you're able to do some of the thermal in Simulink instead if you want. So it's not just using a lumped model now. And we can see if we go back to this that it's effectively just a lump model in Simulink at this point, but it could be part of a wider system of cooling architecture. So I've transferred the lump model from Python into Simulink, and we can run that script. There's a bit of setup to go through to get Python and MATLAB talking to each other. But you can see here that the objects have been regenerated. There's a little note: when changing the Python script, please restart MATLAB for changes to take effect. And then now it's running the simulations. And if we were to go back to the scope inside the simulation, yeah, it's finished already. I can rerun it, so it's a lot quicker the second time you run it, actually. That's gone. Alright, that disappears. We get to run it here. So this is obviously quite a small system. I'm taking, I think, a 10-second time step again. So we've got a little bit of discontinuity around the changes between charging and discharging. But it's running super efficiently, just for this small problem, in a number of seconds. So yeah, that's something that we're working on, and hopefully should be of interest to quite a few of you listening. So thanks for your attention, and now we'll have some videos about some of the Google Summer of Code projects that we've been contributing to. So thanks.
Hello everyone, I am Priyanshu Agarwal. I was a Google Summer of Code student at PyBaMM, and my project was related to printing formatted equations in PyBaMM. So in this session we will look into using LaTeX to render the expression tree PyBaMM uses into human readable format for better visualization. So let's import PyBaMM first. Now let's first look into some simple equations which are easy to get. Now let's visualize this equation into a form of an expression tree. So this is what the expression tree for the equation we just wrote looks like. Now let's look into the other functionality, which is called the toEquation. So if I do equation dot toEquation, it will convert all the nodes of the expression tree into simple objects and give LaTeX. But in case of models, the expression tree is much more complicated. For example, in the case of single particle model, the expression tree would look something like this, and it is hard to calculate each leaf node manually. So for that, we will use LaTeXify. So let's load a model first. Now we will run the LaTeXify method. And it will give LaTeX. Now the LaTeXify has various parameters, and one of them is the new line parameter. So if I write new line equal to false, so it will return all the equations in a form of list without the new lines, and it contains all the properties and inherits all of the properties which list has, and they can be sliced too. So let's say, for example, I want the fifth equation of this model in this list. So if I slice it, I will get the fifth equation of the model, and if I convert it into a string, it will give me the LaTeX of that particular equation. Now let's look into the other functionality, which is the file name. For that, let's take another bigger model for the demonstration of it. It may take some time. Yeah, this particular argument returns everything in a file format which we specify. So Now if I look at this file, so it includes the model equations, the initial and boundary equations, all the concatenations, the voltage expression, and all of them includes ranges in front of them wherever applicable. And at the bottom we have all the parameters and variables used in this equation for reference. We also have an example notebook which have all the step-by-step procedure on how to use LaTeXify. For that, let's go to GitHub and then the PyBaMM repository, examples, notebooks, models, and the file with the name LaTeXify. So you can refer this notebook for more details on how to use LaTeXify exactly. Now we came across various edge cases during the process of converting them in LaTeX. So if you see one, please feel free to open an issue in PyBaMM or contribute to it. And if you face any issues during the installation process, please report it. So that was all. Thank you.
Hi everyone, I am Saransh, an undergraduate at University of Delhi, India, and I was a Google Summer of Code student under PyBaMM this year. So my project was about creating a Twitter bot that could run battery simulations and could also maybe reply to some of the simulations, some of the requests from users. It obviously used PyBaMM as its backend for all the battery stuff, so you can go to the main repository and star the repository to support the overall development of the package. To go to my to actually see my project live, you can go to badbot underscore on Twitter, and there you will find out how the bot is tweeting every day at I guess 7 a.m. and 7 p.m. UTC by plugging in different models, parameter sets, degradation modes, etc. It tweets some plots, summary variable plots, and as well as some GIFs uh, for to show the time dependent variables, to show the variable that depends on time and x together more clearly. The code for the bot is available in the badbot repository under the PyBaMM team account. If you encounter any bugs or any issue, you can go to the issues tab, or if you have any new feature request, you can go to the issues tab and create one. Or if you want to contribute to the repository, you can go through the readme file. The bot also stores all the configuration that it is tweeting out. All the configurations are stored in data.txt file. So right now the bot has tweeted out 123 random simulations, and the latest one is stored in the config.txt file. You can use these configurations to actually recreate the simulation by either cloning the repository and running this run simulation notebook, or by going to Google Colab and running this notebook on the cloud. So the first cell is meant to install PyBaMM and import all the necessary packages. The second cell is the one that retrieves the latest configuration from the config.txt file. So opening the bot for reference, the latest tweet is about comparing single particle model by varying the electrode width, and you can also play with this configuration by actually updating them here, the config dict, or you can run an older configuration by overriding the config dict value here. So by just copy pasting a configuration from the data.txt file. This cell is meant to scale functions which won't be necessary right now. This cell won't give any output as the latest tweet wasn't about plotting summary variables. The next cell should give an output, and it should be identical to this one, as this is about comparisons with no experiments, and it does give an identical output with a slider plot version. You can again play with this more by changing the config dictionary up, and the leftover cells won't give any output because this cell, for example, is meant for configurations with the experiment, and the latest tweet wasn't an experiment didn't have an experiment in the configuration, but it would give an output if you had an experimental configuration. So if you can actually copy paste a configuration with the experiment and paste it here to run that particular cell. Other than that, the bot is also capable of replying to some particular simulations, and the best way to get started with it is by exploring the request examples markdown file, which is available in the badword repository. The best way to actually start with this feature is by copy pasting a dummy or a sample example and tweeting it out. If I, for example, tweet out this particular configuration, then the bot should automatically pick that up. This part of the bot is deployed on Heroku, so it does take time for the bot to reply on an average around 10 to 15 minutes, and it can't handle heavy simulations right now because Heroku does put a memory condition on all the deployed apps, and the cutoff time is 20 minutes. So if your simulation exceeds 20 minutes, it will automatically cut it off and won't give the desired output. It would give an error which would be tweeted out as a reply on a tweet. So the bot actually read the configuration here, the tweet here, and automatically generated a configuration related to that tweet and is now processing the appropriate reply. It would take around 10 to 15 minutes for the bot to reply. To read more about the complete project and how I went through it, what all pull requests I made, you can go through the final report, which is much more detailed. And it also contains links for all the blogs that I wrote, which are available on my Medium account. Again, you can reach out to me on GitHub or on Twitter. And after around 10 minutes, I tweeted it. I tweeted the tweet at 7:45, and it is 7:55 right now. So after 10 minutes, the bot replied with the requested simulation. And a general tip would be right now to not give some complex simulation or some heavy simulations to the bot as that might result in crashing of the deployment, as Heroku gives us very limited space and the bot has to create around 80 plots and go through all of them to create a GIF. That requires a lot of time and space. So that would be it. Thanks.